Welcome to this session on physics. In this session, we are going to talk about the physical gas laws that form the foundation for hyperbaric therapy. I'm Dr. Bob Bartlett, and in this session, we are going to review the following concepts. We're going to talk about pressure and temperature and how these are important for our patients in the chamber. We're also going to review the various gas laws: Dalton's law, Henry's law, Boyle's law. And although many of these may sound unfamiliar to you, by the time you finish your curriculum here, you will know exactly what each and every one of these laws mean. And by the way, they're called laws. They're not guidelines, they're not recommendations. They are gas laws, which means they are inviolate, absolute. So let's get started here. The first concept we're going to talk about is pressure. Pressure is a fairly straightforward concept. It is defined as force per unit area. And yet, there are so many different ways we can express this simple concept. For example, there's atmospheric pressure, hydrostatic pressure, absolute pressure, gauge pressure, and partial pressure. So what do all these terms mean? And if we look at a gauge on the side of a monoplace chamber, what do these letters mean? We see in the center of this gauge PSIG. We also see that there is an inner ring of numbers. What do these numbers mean? And there are also an outer ring of numbers. We'll come back to this gauge at the end of the session, and you'll be able to tell me exactly what all of those numbers mean. And the same is true for the letters. If we look at a multiplace chamber, we would find it has an entirely different gauge. This gauge is calibrated in feet of seawater. You may wonder why there are two different gauges. That will become clear to you later on in training when we talk about decompression sickness and multiplace operations. But for right now, my job is to demystify this whole concept of pressure and to give you a better understanding. So let's take a little closer look here at this concept of atmospheric pressure. We live in an ocean of air, and in this ocean of air, we are the bottom dwellers. And right here on the bottom, as you can see, the pressure is 14.7 pounds per square inch. Now, we could go up about 18,000 feet, and we'd find that the pressure is cut in half. From there, we would have to go up several 100,000 feet to exit into the vacuum of space itself. But we could also express this same pressure using a different term. For example, if we were a meteorologist, we would talk about pressure in terms of millimeters of mercury. The forecast for the New England coast calls for stormy weather. The mercury is 29 inches and dropping rapidly. We expect heavy storms. Well, that would be the meteorologist's way of talking about pressure. That same forecast in Europe, they would give it in millibars. And because we're going metric, many people might refer to it in pascals or kilopascals. And for those of us trained in the biological sciences, we would typically speak of it in millimeters of mercury. 760 millimeters of mercury is also equal to sea level pressure. So let's look at this other concept, hydrostatic pressure. What exactly does this mean? Well, it's the same unifying concept of force per unit area. But in this case, the force is expressed as feet of seawater. We know that every 33 feet you go down into the ocean, you add one additional atmosphere of pressure. So starting at the surface, sea level, a depth of 0, there is one atmosphere, which is the baseline pressure of the gas above the ocean. If we go down 33 feet, we add the weight of water to that atmosphere. So we now have 2 atmospheres total. In a moment, we're going to talk about the concept of atmospheres absolute. So every 33 feet of seawater adds 1 atmosphere. That's a key concept, and it's certainly a fact that you will need to simply commit to memory. Now, some of you might also be aware that fresh water is a little less dense than seawater. That being the case, about 34 feet of fresh water is equal to 1 atmosphere. That's a fact that you don't necessarily need to remember because people typically don't speak about feet of fresh water. But as you noticed in that multi-place gauge, it was calibrated in feet of seawater, which is a fairly standard dimension, just like pounds per square inch, millimeters of mercury, and so on. Well, how about this concept of absolute pressure? What is that all about? Well, absolute pressure is really a sum of the atmospheric pressure plus any additional hydrostatic pressure. The best way to think about absolute pressure, it's an absolute accounting of all of the pressures, which means we have to always keep in mind the weight of the atmosphere under which we are living plus any additional pressure. Now, there is another term which is gauge pressure. So what's gauge pressure all about? Well, in the lower right-hand corner of your screen, you see the typical kind of pressure gauges one might encounter in a hospital. I'm sure many of you have worked with oxygen cylinders, and these are typically calibrated as gauge pressure. So when the gauge on that cylinder reads 0, is it 0 in an absolute sense? That is to say, 0 means it's a vacuum, it's a completely empty chamber? Well, not necessarily. We know that when it reads 0, it simply means that there will be no more gas coming out of the chamber. But we know that that chamber or cylinder still has a gas in it. So it's not really 0 in the sense of being a vacuum. It's 0 in the sense that it has simply come back to atmospheric pressure. So that's what the concept of gauge pressure is. If the gauge was set against an absolute scale, then 0 would truly be 0, meaning the cylinder is now empty. It is a complete vacuum. So the difference is whether or not you take into account the presence of the atmosphere or you ignore the atmosphere. So it's a difference of 14.7 pounds per square inch. And this is an important point and distinction to always keep in mind. Are we talking about gauge pressure or absolute pressure? Now, we can easily convert between any of these scales. It's just a simple matter of what people call dimensional analysis. For example, we know 33 feet of seawater equals an atmosphere. 14.7 pounds per square inch also equals an atmosphere. So how many pounds per square inch is there per foot of seawater? Well, it's simply 14.7 divided by 33. And it's about a half a pound per square inch per foot of seawater. Now we can easily convert into atmospheres absolute using the same approach. We know every 33 feet of seawater is an atmosphere. So if we wish to talk in terms of depth absolute, then depth absolute must take into account the weight of the atmosphere. So in this equation, we know that depth absolute will be equal to the depth into the ocean plus 33. What is that 33? Well, that's the weight of the gas above the ocean, the weight of our atmosphere. So if we consider a person at sea level, they have a depth of 0 plus 33 feet, which is the weight of the gas or the atmosphere above the ocean, divided by 33 is 1. So sea level pressure is 1 atmosphere absolute. If we were to plunge in the ocean and go down to 45 feet of seawater, then it would be 45 feet plus 33, the weight of the atmosphere expressed in feet of seawater, divided by 33, because there's 33 feet for each atmosphere. And the total is 2.4 atmospheres absolute. Again, just keep in mind, if you want an absolutely correct answer, then you need to calculate everything in atmospheres absolute, and always keep in mind the weight of the atmosphere is a part of that calculation. So what about the next concept here? Partial pressure. What's partial pressure all about? Well, partial pressure reflects the fact that this ocean of air we live in is really a mixture of gases. It's comprised of oxygen, nitrogen, and then a variety of small trace gases. Dalton's law, the next gas law, is a very important law that takes into account all of these partial pressures. It states that the total pressure of a mixture of gases is a sum of the partial pressures. That is, the pressure that would be exerted by each gas if it was acting alone. So in the case of our atmosphere, if you were to simplify it, you could say that it's about 20% oxygen, 80% nitrogen, and these two partial pressures must sum up to 760 millimeters of mercury, or 14.7 pounds per square inch. So let's look at this more closely, this concept of Dalton's law. Because later on in the course, we're going to use Dalton's law to look at specific gases. For example, most of our interest will be focused on oxygen. So we'll really want to know what is the partial pressure of oxygen. We really don't care what the partial pressure of the other gases are because the gas that we're typically interested in is oxygen. But sometimes, in the matter of decompression sickness, we might be more interested in the partial pressure of nitrogen. So in this diagram here, looking at this concept, we see that we have 20% oxygen, 80% nitrogen, sums up to a total of 100%. Expressed in partial pressures, it would be 0.2 ATA plus 0.8 ATA for nitrogen will give us 1 ATA in accordance with Dalton's law. Now let's examine what happens if we pressurize this air. If we double the pressure in the air, you'll notice here that the percent of the gases remain the same, but the partial pressures change. Why? Well, air is air. Whether you compress it or not, you really don't change that composition. So it's still 20% oxygen. But because you're now at twice the pressure, you'll notice that the partial pressure of oxygen has increased to twice the previous amount. It is now 0.4 ATA, plus nitrogen 1.6 ATA sums up to the new pressure of 2 ATA. If we come down here and examine what happens at 3 times base pressure, or 3 ATA, again the percent oxygen is still the same, 20%, but now you notice the partial pressure of oxygen is 0.6 ATA. So when we compress air to 3 times sea level pressure, we have a partial pressure of oxygen of 0.6 ATA. And the only way that you could achieve 0.6 ATA under normal conditions is to actually strap on a mask that's 60% oxygen at sea level, or take air and compress it to 3 times sea level pressure. Both would physiologically give you a partial pressure of oxygen of 0.6. Now we can continue on here at 4 ATA and so forth. Again, the sum of the gases must always equal the new pressure. And of course, the percent of oxygen doesn't change because air is still air. So let's take Dalton's law and put it into use. What is the partial pressure of oxygen in the saline rinse? We use a lot of saline irrigating our wounds in the clinic. So how much oxygen is actually dissolved? Well, with Dalton's law, we can answer that question. We know the gas fraction times the total pressure. The gas fraction here in the atmosphere is 0.21 if we wanted to be really precise. So 21% or 0.21 times atmospheric pressure at sea level, 760 millimeters, gives us the following result. There's 159 millimeters of oxygen pressure dissolved in that saline rinse. Well, how about if we wish to express this a different way? What's the partial pressure of oxygen in pounds per square inch? Again, the same principles apply. We know the gas fraction, 0.21 times the total pressure. Only now we express that total pressure as 14.7 pounds per square inch. Multiplied times 0.21, this gives us a new answer, which is 3 pounds per square inch. So the partial pressure of oxygen in that saline rinse is about 3 pounds per square inch. The next law I'd like to examine is Henry's law. Henry's law is a very important law because it governs the solubility of a gas in a liquid. In our previous session on the history of hyperbaric therapy, we examined Barima's bold experiment of life without blood. And this whole experiment was based on Henry's law. How much oxygen could you dissolve into the plasma? Well, Henry's law can help give you that answer. We know the volume of gas within the liquid is a function of a solubility coefficient and the pressure of the gas above the liquid. So if we look at this diagram at 1 ATA and we double the pressure to 2 ATA, we will simply force more gas into the liquid. And Boerema clearly understood that concept. The only question was to subject it to empirical examination, which indeed he did, and he demonstrated that yes, it is possible to exist in the absence of red cells. The next law I'd like to look at is Boyle's law. Boyle's law is a very important law because Boyle's law is a reflection of gas volume as a function of pressure. Boyle's law states that the volume of a gas varies inversely with the absolute pressure. So if you imagine a balloon and you increase the pressure around the balloon, it will get smaller. If we decrease the pressure, it will get larger. Now, mathematically, as you can see in the diagram, we can express this as P1V1 equals P2V2. In other words, the product of pressure times volume must always equal the new product of pressure and volume. Some people will write this equation in a simpler fashion, which is P1V1 equals K, or a constant. Either way, it's pretty simple to apply Boyle's law to figure out what the change of volume might be. Later on, we're going to look at Boyle's law and the clinical implications under the concept of barotrauma, the direct clinical application of Boyle's law for the various air spaces in the body. For example, the middle ear, the intestines, or the lungs are all gas spaces that will be subject to Boyle's law. Let's look more closely at Boyle's law. In this table, if we look at gas volume of a balloon, let's say that it is 1 cubic foot in volume. As you'll notice here in the second column on the right, we are at sea level pressure, 1 atmosphere absolute that we could also express as 14.7 pounds per square inch absolute. We take that balloon and we plunge it in the ocean down to 33 feet. Because we have doubled the pressure, we will half the volume in accordance with Boyle's law. Now from 33 feet, as we go to 66, there is an incremental reduction from a half a cubic foot to a third of a cubic foot. But we have to go all the way to 99 to cut that half cubic foot in half again to 1/4. And the next time that we see a halving of the volume, we will have to go down well beyond 165 feet. So where is the greatest change in volume occurring? Well, it's occurring right next to the surface. The biggest change is with the initial compression. Now, there's an important clinical correlation to keep in mind about this. You will discover this in practice. Given this observation of Boyle's law that the greatest pressure volume change occurs within the first few feet, What do you think that means in practice? Well, when we look at barotrauma and how, for example, it affects the middle ear, if patients are going to have trouble with their ears, do you think it will be in the first few minutes of compression or the last few minutes as they reach the depth that they're headed to? Well, you're right. It'll be the first few minutes. That is the most important time because there's the greatest pressure volume of changing within the first few minutes. So let me just share with you a clinical illustration of this importance. At a particular hyperbaric program, there was a patient who had too much oxygen. They had an oxygen seizure. You may recall when we talked about the history of hyperbaric medicine that we referred to this Baer effect, the realization that too much oxygen might have adverse effects. And one of them can be an oxygen seizure. We'll talk more about oxygen toxicity later in the course, but for now I just wish to illustrate a point about Boyle's law. The patient was at 2 ATA when they had this particular problem. So the chamber is sitting at about 15 pounds positive pressure by gauge, and following the seizure, the nurse began to decompress the patient. They summoned the physician, and they were decompressing 15, 14, 13, 12, 9, 8. About the time they got down to 5 pounds per square inch gauge, about a third of an atmosphere, the physician burst through the door, said, "What's going on?" He said, "Well, the patient's had an oxygen seizure, and we've been decompressing here at about 1 pound per minute." And he said, "Well, where are you?" He said, "Well, we're all the way down here to about 5 pounds. So we're almost back to the surface." Well, at that point, being concerned as he was, he directed the staff to press the red button. Well, in the operations session, you'll learn about the mysterious red button, but on this particular chamber, the red button is an emergency vent button. So when you press the red button, how fast do you decompress? You can decompress at about 1 pound per second, 60 times faster. Well, of course, he's out of the chamber then in 5 seconds. Fortunately, nothing happened to the patient. When I called the physician later, though, to review the case, I was greatly concerned by the fact that they had used the emergency decompression button. And I asked him what he was thinking at the time. He said, well, he was very concerned about the patient's welfare and he wished to get them to the surface as soon as possible. And because they had already decompressed 2/3 of the way and there was so little left, he thought there was no harm. Well, I guess he had kind of forgotten that observation about Boyle's law we talked about just a few minutes ago. The fact that the greatest pressure volume change is occurring right near the surface. So really it's the last few pounds of decompression that pose the greatest risk because there is the greatest pressure volume change. Now you may say, well, what's the risk? Well, the risk is that if this patient didn't have a completely open airway, if they had some mucus plugging or any of a number of different scenarios, there's a possibility if they couldn't vent their lungs fast enough, they could possibly burst an alveolus and develop a pneumothorax. Again, we'll talk about that under the concept of barotrauma, but for now, appreciate the fact that Boyle's law is this relationship of pressure and volume. And it is a very important relationship during the first few pounds of either compression and decompression. If we examine this concept of Boyle's law from another perspective, again, looking here at a bubble at the surface, you'll notice that when we go down to 33 feet or 2 ATA, again, we cut that bubble volume in half. But if you look closely at the column on your extreme right, you'll notice that the diameter does not change by half. There's only about a 20% reduction in the diameter, but we have cut the volume by 50%. And mathematically, for a sphere, volume and diameters are not one and the same. Although they are interrelated, they are not one and the same. So what is the clinical point? Well, later, when we talk about gas emboli, some people believe that the biggest benefit of HBO is that we take these bubbles and we compress them down, which indeed we do. But when we double the pressure in a hyperbaric chamber, do we actually obliterate these bubbles? Well, we'll come back to that concept a little later, but for now, remember that we may cut the volume in half, but there's only a 20% reduction in the diameter. So let's take Boyle's law and put it into play. Let's assume that we have a balloon with a volume of 24 cubic feet. If we submerge it into the ocean, what would the new volume of the balloon be at 33, 66, and 99 feet of seawater? It's important that you feel comfortable doing these sorts of calculations. Not that you'll need to do them every day with your patients, of course not. But if you sit for some of the certification exams, for the physicians, for the board certification, or the certification from the American College, for the nurses sitting for the Barometrical Nurses Association, or for the technicians who are sitting for the NBD HMT exam to become a certified hyperbaric technologist. These will be very typical of some of the questions asked on those exams to determine if you really understand the concept. So let's come back to this example and figure out what the volume would be. At the surface, 24 cubic feet. Well, here is Boyle's law. Pressure and volume on one side must equal the new pressure and volume on the other side. Rearranging, we can solve for the new volume, or V2. The initial starting pressure is 1 atmosphere, we're at sea level, and the initial starting volume is 24 cubic feet. So now we wish to determine what is the new volume. Well, the new volume is related to the new pressure. The new pressure can easily be determined in the following fashion. We know that every 33 feet equals 1 atmosphere. To get an absolutely correct answer, we need to change everything into atmospheres absolute, which means that we add the weight of the background atmosphere, 1 ATM, plus 33 feet of water, which is also 1 atmosphere, is 2 atmospheres absolute. So substituting this new value, 2 atmospheres absolute, we find that the new volume is 12 cubic feet, or precisely 1/2 of the original volume. Well, how about if we consider what the volume would be at 66 feet? Again, we do the same kind of relationships, except in this case, it is 2 atmospheres of water plus 1 atmosphere of air above gives us 3 ATA. So the new volume is actually 1/3 of the original volume. Well, how about at 99 feet of seawater? Again, same method and approach, and the new volume would be 1/4. Now, some of you may have already made the observation that if I take the starting pressure, sea level of 1 ATA, and I put the new pressure right under that, in this case 4 ATA, then I take the original volume and multiply it by 1/4. So if the second pressure was 8 ATA, it means that the new volume would be 1/8. Well, how about if it was 16 ATA? Well, then it would be 1/16. So that's a quick way or a shortcut for Boyle's law. But again, Boyle's law is a very important law. It affects our patients every day we put them in the hyperbaric chamber because of the various gas spaces, the middle ear, the sinuses, the intestinal tract. So we'll look at Boyle's law in greater detail later when we talk about barotrauma.